All right, we want to talk about a worked example using the ideal gas law and just see the kinds of weird little things that come up. So imagine you have a gas cylinder. All right, there it is. And we're going to fill this thing up with nitrogen. And we're going to make sure that once it's filled, it's at room temperature. And when all that is done, what we have is a 30-liter gas cylinder, meaning there's 30 liters of gas. We know in this case, the mass, obviously the cylinder is very heavy, it's a big piece of metal, but when you filled it up, we noticed the mass went up 5 kilograms. So we know the mass of the gas in here, the gas itself is 5 kilograms, about 10 pounds, and then at room temperature. So we're assuming all of these things are true. 30 liters, 5 kilograms of mass at 20 C. So we want to use the ideal gas law, and if I could, maybe I'll just sneak back to this side really quick. There it is. All right, and so we probably are going to focus on this one because this has physics units for us. Here was the assumptions. You can go back and watch if you want to know what happens if those assumptions aren't valid. That's great. There's all the information we had in the last video. So notice when we're doing this problem, joules is kind of the key. When I think about joules, I know a joule is a Newton meter. So that makes me think I want to talk about, and a Pascal is a Newton per meter squared. So in order to get joules over here, if I have this in pascals, that's newtons per meter squared, I'd need meter cubed here to get a joule. So I want my volumes for physics problems usually in meters cubed. All right, so let's go back to here. So we want meters cubed. So for part A, what do we have? We have 30.0 liters. Now you could use a Google converter for this, and in the real world you probably would. But just in case, let's figure this out. I know that 1 centimeter cubed is 1 milliliter. All right. Well, that doesn't quite match up because this is in units of liters. So maybe I better throw in the fact that 1 milliliter is 1,000 milliliters is 1 liter. And then finally, I know that 100 centimeters is 1 meter. But then because this is cubed, we better cube all of these, including that number there. And notice you essentially get 10 to the third over 10 to the sixth, because this is, right, 100 cubed is a million. So it ends up being, this whole conversion ends up being divide by 1,000. 1,000 over 1 million, that's, so to convert back and forth, you could remember that. Or you could just do this conversion process. So we're going to get 0.0300 meters cubed. All right, divide by 1,000 to get liters to meters cubed. All right, part B, number of moles. I'm going to look this up on the periodic table, and maybe I'll show you this really quick. Let me blow this up, scoot over here and share a screen. Just a second, here it comes. So if you look at the periodic table, you'll see some numbers in here. This number means grams per mole. All right, so, and that's for 1 atom of nitrogen. Now think, we have 2 atoms because nitrogen is diatomic. If you didn't know that, now you do. N2 is typical form of nitrogen. So when you multiply this number by 2, oh, look, it happens to be written right here on the screen. 28.014. All right. So we know the molar mass is 28 point, oh, I forgot what that number was. 014 grams per mole. So that's what you get off the periodic table. Now, if we go back to board 1, if you recall, come on, we can use this relationship to get the number of moles. We know the mass of our sample is 5. We know the molar mass from the periodic table. We can get that. So let's go back and do it. Maybe today. I just changed these batteries. Okay. So we know that N is equal to M over big M, which is, and I think I worked this out. Let me just grab the number. 178.48 moles. Oh, and so, well, this was, notice the issue that you're going to have. This is in kilograms, that's in grams. So why don't we change this one to grams? Right, and so out of all that, I got 178 point change, 48. All right, that just barely fit. Oh, I can fit it in there, sorry. Trying to make sure this fits on the screen while I'm writing it. It's hard to see from across the room. Okay, so that's how many moles we've got. All right, in this case, what's part C? Number of gas molecules. Recall, the number of moles is equal to the number of molecules, capital N, divided by Avogadro's number. All right? And sometimes this will have a unit of 1 over mole put on it. So maybe I'll write this in this way. Some people will write that as 1 over mole. When you punch that in, what is the number of molecules I got? 1.0748. .07, whoops, 748. And I guess we don't need a unit on that because it's just a number, right? And to be clear, that's N. So if you just cross multiply, you'll get N is about 10 to the 26th. All right. The pressure inside the gas cylinder. Finally, we get to the ideal gas law. PV equals nRT. We want to use the physics R because we're using meters cubed, et cetera, et cetera, et cetera. All right, so in this case, the pressure is nRT all over the volume. Watch out! Can you use degrees Celsius? No! Ah! We've been using degrees Celsius in the last chapter because every single equation in the last chapter had a delta T. Change of 30 Kelvin is a change of 30 Celsius. But 20 degrees Celsius is not 20 Kelvin. So we have to do our conversion. So to get there, temperature in Kelvin is temperature in degrees Celsius plus 273.15. All right? And so in this case, we could use the number of moles which was 178.48 mole. R, that's 8.314 joules per mole Kelvin. The temperature is going to be 293. And actually, I think we're good to this. And that's Kelvin. Make sure that shows up. It's kind of crappy. All right, when we're adding, this one's off in the tenths column. When you add, you keep the column. That's why we got 4 sig figs on there. And then the volume. What was the volume? Somewhere we had that. All right. So in this case, we can see that we're probably going to end up with 3 sig figs. We crank this out. Where's my calculator? There it is. Let's punch it in really quick. 178.48 times 8.314 times 293.15 divided by 0.03. All right, and so I get a pressure of, I'm going to write this in scientific mode. So mode, scientific, quit, second answer, 1.4500 times 10 to the 7th. What units? Remember, the whole point of doing this, in these units, if we used joules, meters cubed, pressure is in Pascal, where a Pascal is a Newton per meter squared. Okay, so this would be Pascal. And we're off in the 3rd sig fig. Keep an extra digit because the first digit is 1, keep an extra digit. All right. Gauge pressure and correction. So if you don't know what gauge pressure is, let me talk about that very briefly. Imagine you put a gauge on here. So you have a gas cylinder and there's a gauge on there. All right. What does the gauge read? It reads the pressure difference, so it's a pressure difference. In this case, if we have atmospheric pressure outside and the pressure of the gas, sometimes this is called P absolute. Okay, P naught is atmospheric, and then there's the pressure of the gauge. So the gauge pressure is the pressure difference. So if we call this absolute pressure, absolute, we could figure this out, I guess, where am I going to squeeze this in? All right, right here. Pressure of the gauge is equal to pressure absolute minus atmospheric in this case. Now, obviously, you can use some pressure other than atmospheric, but in this problem, we were told it's standard atmospheric outside. So in general, just think of a gauge as a pressure difference, and that works the same as a vacuum, right? You could have the difference between atmospheric and the pressure inside a vacuum chamber. So in theory, you could actually slap an absolute value on here if you wanted to, but the other thing to do is just know which pressure is bigger and always write the subtraction that way. All right. So in this case, what does the gauge read? Let's subtract off. So I'm going to do that. Minus atmospheric, which is, remember, atmospheric pressure, we were told, 1.013 times 10 to the 5th Pascal. So it's going to be a small correction, minus 1.013 EE5, so 1.4399. Is that right? So notice, if you have this much pressure, the gauge is actually only going to read that much. But notice it's off by 1 in the third sig fig. Percentage-wise, you can do the math on this and just say, oh, well, what's P naught out of the absolute pressure? So if you look at this, P naught out of P absolute is about 0.07, is that right? 007? I think I worked this out. Oh, 0.07%. It's off by about 1%. Wait, is that right? Let's see, I think there might be I'll check this number. Should be a little bit less, all right, I'll check it right now. Atmospheric 1.013 EE5 divided by 1.45 E7. Okay, and then divide by 100. Or whoops, times by 100 to get to a percent. 0.7. So it's about 0.7%. Right? 1 out of 100 is 1%, so 1 out of 150 is a little less than 1%. All right, and I think, one last question. How would the answers change if we use helium? Okay, I was gonna say something more about the gauge, whatever. In this case, how would the answers be different? Think, pause the video and just say which of these would change, which wouldn't, blah, 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 blah. 3, 2, 1, here we go. Well, the volume would be the same, but the molar mass would be about 7 times lighter, right? So in that case, you should have about 7 times as many moles. Right? So you'd have almost 1,000 moles. If you have more moles, that's going to propagate. If you have 7 times the number of moles, you should have 7 times the amount of pressure, and the gauge would make even less of a difference. All right, so great. If you're blowing up balloons with nitrogen or helium or something like that, or if you have a CO2 tank, you can read the gauge and you can trust the gauge, even though there should be a small correction. It's negligible. It's a percent or so. I think that's enough on just kind of getting used to the issues. Always watch out for that temperature. You got to use Kelvin. Got to use Kelvin. Watch out for your units, grams, kilograms, etc. And we want Pascal.